Imagine a vast map of isolated points. Right now, they exist cut off from one another, drifting without a way to communicate or share resources. Whether these are rural villages needing paved roads or massive data centers routing internet traffic across a continent, the objective is the same: weave these isolated points into a single, unbroken network. But in the real world, connections are never free, and they are rarely equal. Every potential link between 2 points carries a specific physical cost, or in graph theory, a weight. The mathematical structure we are striving to build is called a minimum spanning tree. This is a specific type of network that successfully connects every single node on the board, with absolutely zero structural redundancy. The word minimum here is strict. It means the structure must yield the lowest possible total sum of all its connecting edges. Achieving this is an optimization puzzle. Finding the absolute cheapest total path out of millions of possibilities requires rigorous mathematical strategy, not guesswork. We already know one highly effective way to solve this: Prim's algorithm. Prim selects a single starting vertex and continuously grows a unified tree outward from that central root. Kruskal's algorithm takes a different path. It entirely abandons the concept of a starting vertex. Instead, Kruskal operates purely as a greedy algorithm. A greedy strategy means the system evaluates the board and makes the immediate, locally best choice available at that exact moment. Rather than expanding outward from a central hub, Kruskal scans the entire map and grabs the absolute cheapest edge, regardless of where it lies. By dropping the requirement for a central starting point, the algorithm builds multiple disconnected fragments at once. Over time, these disparate components will snap together into a single network. But a greedy algorithm cannot function on disorganized data. It requires a specific structure to identify which choice is actually the cheapest. Here we have a scattered set of edges and their weights. The mandatory first step of Kruskal's is to arrange this data into a sorted table, sequentially ordered from the lowest weight at the top to the highest at the bottom. With our data ordered, the execution is mechanical. We look at the top of the list and select the lowest available edge, AB, with a weight of 2. That edge is drawn. Our first 2 nodes are successfully connected. We move exactly 1 slot down the table. The next lowest is BC, carrying a weight of 3. This edge is added to the graph. Next is CD, weighing in at 5. We pull it from the list and add it to the board. Following the list in order builds the network 1 piece at a time. However, as edges are added, the risk of creating redundant connections increases. Moving down our table, the next available edge is AC, with a weight of 6. Since 6 is the next lowest number, the greedy rule suggests we add it. But as the visual shows, adding AC creates a closed loop that invalidates the spanning tree. This enclosed geometric shape is a cycle. It allows you to start at node A, travel through connections B and C, and return right back to where you started. A valid spanning tree cannot contain cycles. Any closed loop represents a redundant alternative path, which means the total cost is no longer at its minimum. The algorithm must reject edge AC, discard it entirely, and move to the next item on the list. This demonstrates the trade-off in Kruskal's approach. While the greedy choice identifies the lowest cost, the algorithm must also verify the structural integrity of the tree by preventing these loops. As humans, we can easily spot a drawn loop on a screen, but a computer doesn't process spatial geometry. It needs a mathematical way to detect a cycle. This is the union find, or disjoint set, data structure. It acts as the cycle detection mechanism for Kruskal's. At the very start, every single vertex exists in a state of isolation, assigned to its own unique group. We can track the build through this structure. When we accepted that first AB edge, the system performed a union operation, causing the separate boxes for A and B to merge into one unified set. When we added the BC edge, that set expanded again. Now A, B, and C all belong to a single overarching group. The second component is the find operation. It identifies which specific group a node currently belongs to. Let's apply find to our rejected AC edge. The computer asks, what is the group for A and what is the group for C? Because both A and C are in the same merged box, find returns the exact same result. This establishes the rule: if find of X equals find of Y, the nodes are already connected. Adding a direct edge between them would create a cycle, so the edge is dropped. Union find allows the computer to process connectivity as a series of set membership checks. It replaces visual inspection with a fast mathematical operation. With cycle detection running, we pass over the rejected edge and add the next lowest option from our table, DE, with a weight of 7. The algorithm stops the search once it has selected n-1 edges, where n is the total number of vertices on the board. This visualizes the process. Sort the edges, pick the smallest, check for cycles, reject if found, otherwise add the edge, merge sets, and check the target count. In pseudocode, this maps out exactly the same way, providing a template for code. To remember the sequence, you can use the mnemonic SSCUCR: edges, sort, smallest, cycle check, union, and repeat. Building an optimized network is a matter of repeating these simple logic checks until the structure is complete. Once the target edges are selected, our minimum spanning tree is finished. The sum of those selected weights represents the absolute minimum cost to connect every point. Looking at both methods, we see clear architectural differences. While Prim's algorithm expands from a single vertex, Kruskal's merges disconnected components across the entire graph. Prim relies on priority queues to track its expansion, while Kruskal requires edge sorting paired with disjoint sets. A common point of failure is neglecting to sort the edges before making a selection. Without an ordered list, the greedy strategy cannot correctly identify the minimum weights. Another mistake is attempting to start the process from a specific vertex. Kruskal's requires that all edges be evaluated equally, regardless of their location in the graph. Formally, Kruskal's algorithm is a greedy algorithm that constructs a minimum spanning tree by selecting the smallest weight edge that does not create a cycle. The algorithm functions through a specific interaction between the greedy selection of edges and the constraints of cycle detection. By applying these rules consistently, the system identifies the most cost-efficient way to connect every node in a network.